see you guys are on camera just for information.
On Thursday, we have class from 4:30 to 5:30. And that's also another time that we can do it.
Okay. Hello guys. Hey, so we are missing someone, right? 1, 2, 3, 4, 5. Oh, right. Yes. Yeah. Right. Yes. Okay. Yeah. But, okay. We can always use the recordings. So we have homework 1. No, homework 1 was due. How did the submissions go for those who are across Travis, Matt, and Curtis?
It was okay. I uploaded it just a little bit ago. I used Office Lens on my phone to scan it, so.
Okay, so it worked smoothly. Is there a way to directly upload it from the phone to the D2L? That was a question that came up.
Not that I've found easily. So like the way that it works is I have it linked to OneDrive, so it just uploads it to my files through my school account, and then I download it and upload it from my computer.
Okay,
So
that is a 2 to 3 steps process. Yeah, that's what everyone was.
Yeah.
Matt, how did it go?
It went well.
Okay. Curtis?
It worked fine for me. I just like emailed the pictures to myself and submitted it in detail.
Okay, exactly. That's what others were saying too. So yeah, I don't know. I don't use it. So you guys know better. Okay, so there's a new homework that has been posted. Homework 2, that's due Monday. Same idea, it'll be due on D2L. This is on vector differentiation. And there's a homework 3 that has also been posted. This is not due, but that doesn't mean that this is not important. It's on vector integration. And this is what you study in a lot in the Cal 3, I think. So refresh stuff in Calculus 3, I think. Is this math 251? I think. I'll just look it up. It is. It won't be very significantly important in our course. The ideas are very important, but we won't use it so much because we will be using most of our equations in differential form. So that's a primary difference between what we have studied in the introductory level physics, electrodynamics, or electromagnetism, and this course. It will be mostly differential equations instead of integral equations that we used earlier. So I have made a homework. You should look into it. You should be able to do those problems, especially there will be a question asked in your exam based on this homework, but I'm not making it due. That is the only difference, so that I can basically skip over the subject. Otherwise, I have to spend 2 lectures doing a lot of problems on it. So that's the main idea. There will be one more homework due before the, or let me not, as time comes, let me do that. There's midterm 1, which is on September 11, which is a Friday. Any questions or comments on the logistics? Okay. So we want to, as I said, want to talk about vector differentiation, and there are a few things that comes in. First of all, what is the gradient operator? That's that will play an important role in our course. So that's how it is. That's the gradient operator. That in itself has a meaning, but often we write it in some coordinates. If it is written in rectangular coordinates, this looks like d by dx plus j hat d by dy plus j hat d by dz. It acts on a scalar function. It can also act on a vector field if you want a vector that is dependent on spatial points is called a vector field. So this will be called a gradient operator. Let's say. And just to emphasize that it doesn't have to be in the rectangular coordinates, let me also write it in spherical polar coordinates. So this is d by dr plus theta hat times 1 by r times d by d theta plus phi hat times 1 over d phi, right? So that's the gradient operator in rectangular and spherical coordinates. If we have just a function which depends on any point in the 3-dimensional space, so let me say use R here. So it depends on x, y, and z. That's what it means. So every point in space has a functional value associated with that. This we will call is a scalar field. It's pretty much a function, a scalar function we can say, but it's called a field whenever it depends on 3 quantities everywhere in space. Instead, if we had a vector at each point in the 3-dimensional space, that's called a vector field. So examples. Example of a scalar field. Anyone? Can you think of examples of scalar field? Some physical quantity which depends on where you are in the physical space, let's say. As you move around, it changes. Gravity. Gravity, yes. That's how you would say. By gravity, what do you mean? Like something more? Gravitational potential, maybe? Yeah, gravitational potential, right? So let's say gravitational potential. Yeah. Anything else? Yeah, electric potential, that's what is going to come. So you guys are ahead. Something from the past, something not in this field, because that's what I'm going to teach you. Right? So gravitational or electric potential. That's a very, very good example, because that's exactly what we are going to deal with. Temperature, right? Temperature is a function of points. I think then we are outside what we are learning. And a vector field is, let's say, in this sense, so it will be gravitational or electric field. So this is like saying you're talking about potential, right? It's a V of R. And this is like electric field or G, right? Vector G. We say it is a constant, but that's only true only when you're close to the surface of Earth. If you go away from it, these things change. So it's a position dependent quantity. In fact, it is 1 over R squared in general, close to a planet or a single mass. And electric field is an example. Magnetic field is an example. So these are all closely related. Can you think of something outside this electric field, magnetic field?
I was thinking like water, like fluids.
Yeah, that's correct. That's exactly, well, flow, right? Flow of it's called flow field. Velocity, fluid flow. Yeah, fluid flow. That's good. Fluid flow V as a function of R. Actually, that is how, that is where this first time was introduced. Before Maxwell introduced his equations of fluid hydrodynamics came before. That's where Stokes and others give contributions to. So that's vector and scalar field. Primarily, we will deal with 3 operations. At least we will give names to 3 operations. There will be more, of course, outside this also. There will be operations. So one is when the vector acts on the scalar field. This is called the gradient. This is called, so this is the gradient operator, but this is the gradient of, that's the terminology that we will use. Next is divergence, that requires a vector field. So this is divergence of E. The vector field. Again, you must have seen this in some form in a course, otherwise this is the basic rudimentary idea. And this is the curve. We introduced the idea of or just a basic notion of what a gradient of a scalar field is. What is this equal to, or what is the intuitive field for what the gradient of a scalar field? Normal to the surface. So, so this represents a function at every point in space. So immediately replace this as function minus a constant. So give it a value because the gradient of a constant is 0. So you ask this is an equation of a surface. So gradient of the scalar field being a constant value. So these are a family of surfaces, and the normal to those family of surfaces is what is the gradient operator. In that sense, that has a lot of meaning. So this is normal to the family of surfaces, because this constant could be anything. Normal to the family of surfaces of constant C, right? So let's say constant. So this is C. So for example, if it was a sphere, you would say these are the family of surfaces. All of them have the same normal vector, right? So it's a family of surfaces formed by a scalar field. That's and that is the primary idea we want to keep in mind. That's the notion or the intuitive feel for the gradient operator that we want to keep in mind. The second is divergence. Again, we want to have an intuitive feel for it. So the question comes, what do we understand by the divergence of a vector field? Very.
It's a source of sink.
Yes, that's exactly correct. We want to see if, so this is evaluated at a point. So because this is, all right. At every point I can evaluate this, and it just checks, is there a charge there or not? And what is a charge? Charge basically creates electric field. Remember that the idea of an electric field is that there is a positive charge and a negative charge. In fact, positive charge is a source of electric field, and it goes and dies or ends into a negative charge. So this is a positive charge. So is it a source or a sink? Either way, it will give you non-zero. For example, if you calculate at this point, if you calculate del dot with E, there is no charge, it's 0. And even before a calculation, you can immediately say that that's will be equal to 0. So that's a physical interpretation of that. And since the point charge is actually a source of the electric field, it seems like there must be a point where everything is originating, right? So that source has this divergent structure, right? So that point is like a big bang where something is infinite there, and then it spreads out from there. And that's the idea of divergence. That's where it gets the name divergence of these field lines. So that's what the idea is. So this is checks if it's a source or a sink. Source or a sink of divergent lines. So now we are going to differentiate between two kinds of sources, source or a sink of divergent lines. And I did not say charges specifically because it is more important in the field lines that it is creating. It is not the charges itself. And why do I say that? Now let's come to the curl. So what is a curl represent? And now for that we have to go into the magnetic field. If you think of Ampere's law, what is the so what creates a magnetic field? Moving electric charges. That's very correct. Moving electric charges or currents. Like good moving electric charges is an important piece, but if you have a continuous flow of moving charges, then you say it is a current. So a current, or more precisely, moving charges seems to create a magnetic field, and that and what kind of field does it create? What is the magnetic field that creates? They're circles, right? So we usually So these are positive charges. So if there are currents, so let's say that's a current wire. So this means that there is a charge moving out of the board. Right? This is, either you can say there is a current, or we can say this is Q times velocity V. So let's say I times dl. The current and the length of the wire, or charge times the velocity of the charge. So even a point charge can be associated a current, and that will be the analog. If that's the case, there is a magnetic field associated with it, and they are circular lines. So it seems like circular lines are created by moving charges. That's a special kind of source then. A moving charge is also a source of certain kind of field lines, which is called a magnetic field in this case. And a stationary charge creates electric field lines which are divergent. So this is a curve, and that's a divergent set of lines, and those are two different sources. So this is a curve, that's the divergence. So here, source or sink of curled field lines. And very soon, probably on Wednesday or Friday, we will explicitly calculate this and see what this structure is. Okay. So that's the gradient, and let's consider to get better feel of this, or get more quantitative feel of that. Intuitively, this is all that we need. That will be the important piece of the whole course, if you want. But let's actually get a more quantitative structure in. For that purpose, let's introduce what is called a dyadic. So just to begin, that dyadic is basically, so this is going to be a unit dyadic. Let's begin by unit dyadic. Unit dyadic is a vector, or it's built on two vectors, so it has two vector signs associated with it. So it's like a tensor of rank 2, so it's a matrix in principle. It's basically a unit matrix, and if you want to look at it as a, so what are its components? So this is component, right? So delta ij are the components of the unit dyadic. So remember, a vector has components. Similarly, a dyadic has 9 components. So these are so the Kronecker delta is pretty much a dyadic in a sense. But this has more information than that, and that is in the following sense. This is exactly equal to I hat plus j hat plus k hat. So now this is an equal sign as far as vector identity goes. This is interpreted as a completeness statement. Completeness relation of 3-dimensional space. What does that mean? Completeness relation means that any vector can be expanded in terms of the 3 unit vectors I, j, and k. For example, if I'm in 3-dimensional space, I and j is not sufficient to expand every vector. So that means it's not complete. So how do we know that this is actually complete? So let's begin with any vector A, arbitrary vector in 3 dimensions. So the claim is that if this is a complete set of unit vectors, then I should be able to expand any arbitrary vector. So we begin by saying, let's say A dotted with 1. That's a true statement. A vector multiplied by a unit dyadic will give me back the vector itself, and that's equal to now A dotted with hat plus j hat plus k hat. So that's an innocent statement as of now. I just multiplied by an identity matrix on the right. But now notice the interpretation. I changed the brackets or the parentheses to identify certain things. This can be interpreted as the projection of A in the direction of I hat times I hat plus the projection of A in the direction of j hat times j hat plus the same k hat. Great. But now, this is a different meaning. Projection of A in the direction of I hat is the x component. This is the y component. And this is the z component. And we do know that if any vector can be represented in terms of 3 components, so in this way of looking at it, this is what means to say that this is a completeness relation. So I having these 3 vectors tells you clearly that any vector can be expanded in that form. This is not a proof that this is actually a complete set of vectors, but this gives us an idea of how one unit dyadic being this gives you the idea or connects with the fact that this is indeed a complete set of vectors. It doesn't prove that this is actually a complete set of vectors. Okay. Any questions on this?
So it doesn't require orthogonality for basis vectors, though, right?
Oh, no, it doesn't require. No, it doesn't require orthogonality at all, because imagine. So, for example, actually, we will. No, not in this course. Yeah, extrapolation. So think of a vector. Work in 2 dimensions. Let's say this is I hat, and let's say that is another vector which is making an angle. Right. Let us say this is at 45 degrees angle. Right. So this is some vector E. Let's call it E1 here, and this is E2. Okay. Yeah. Let me state this better. Okay. In this way of writing, I have used the simplification that they are orthogonal. But the point is, if I were to define, so this is called reciprocal unit basis. Have you guys seen this? Heard about this? Reciprocal basis vectors.
Like, is this dealing with like reciprocal space? Like in
That's
size?
exactly correct. Exactly the same thing. This has to do with it started with crystallography. Like if you want to study crystals, what you do is you see it using X-rays, and what you see on the screen is the reciprocal space of the crystal space. Okay. So for any 2 vectors, you construct another set of 2 vectors. So this is reciprocal now. So this is G2, let's say, and this has a reciprocal vector. This is G1. And what satisfies this relation is the product of E2 times G2 and E1 times G1. So together you can have the same idea, but at this stage, the way I have defined it, it's true only for orthogonal vector. So yeah, so let me be safe. Let's make it simple. So I have used orthogonality here. But the ideas are very general. In fact, it takes you to differential geometry, right? The reciprocal basis is still for let's say discrete spaces. You can immediately take it to what is called differential geometry, which is the language in which general relativity is described. So the ideas are very similar. So we start with the unit dyadic, and there you wouldn't use the vector because it's not very convenient. You will start using the index notation, very full-fledged index notation. Here we are mostly working with three-dimensional spaces, so it's convenient to work with unit dyadics. Okay. So yeah, so let me say that this is actually using orthogonality. Okay. But almost there's a very small change of definition you can generalize. So that means to say that any three unit vectors, as far as they are orthogonal, that's good enough. So this also means that I can immediately say that this is r hat. R hat, so spherical coordinates, r, theta, and phi. They also satisfy this relation. So that's r, theta, and phi are spherical coordinates. Mind you, spherical coordinates, or maybe that also requires a mention, right? So this is your x, that's your y, and that's your z. Axis, that's a rectangular coordinates. And let's say there is a vector R, a general arbitrary vector R. Take the projection of this along the z direction, and let's say this is angle theta. It's projection along the plane xy. So that's angle theta. This is in the plane xy. Looks like this. Hopefully that's clear enough. And this is angle phi. This is angle theta. Now notice in mathematics, you would say this is angle phi. In most of the mathematical textbooks, you would say that's angle phi and that's angle theta. It's exactly swapped, and it seems to be pretty consistent. Most of the mathematics textbook call this phi and this is theta, and all the physics textbooks pretty consistently inside the field do exactly the opposite. We can live with it, but the good part is that there is no arbitrariness inside the field. So, but as a student, you will be doing both. So make sure you switch from one to the other. In this course, this is what theta would be, right? So the angle with respect to z, if it is not pointed out clearly. Most of the time, even your textbook will use this as the definition, so don't get confused with what you, because you come with the vector calculus course or sufficient math courses, so it's very easy to use that. So be aware that that's a difference. So this is angle theta, that's angle phi, exactly opposite of probably what you're studying in math course. This is spherical, There's a similar thing and cylindrical. So this is also cylindrical. We will call it rho hat. Rho hat. So spherical is r theta phi. Cylindrical will be rho hat phi, rho phi, and z hat. And of course, this is also equal to I hat plus j hat. In fact, you can pick any three rectangular, any three orthogonal coordinates as far as it is everywhere well defined on the space, then you can do this. Okay, so that's good enough. So now notice, so now we're going to get an identity here. So we're going to have a nice representation of this unit dyadic in terms of gradient operator and the position vector. So let's try to evaluate. So we're going to evaluate three things. This is the gradient operator and position vector. Is this a scalar or is this a vector or is this a dyadic? If there was an operator, yes, that is a scalar. If there was a dot there, that is a scalar. There's a two vectors. I haven't said anything about what this is, right? So here is how maybe I should, before I write this, let me clarify this a little. If there are two vectors A and B, we have already studied, so this is a dot product. This is a vector product of the, vector product, right? That's what we do, vector product. And now there is a third quantity I'm using, and this is A times B. Okay. Now, this is best. So this is the same as I won't put this, but if you are familiar, this is an outer product.
Is that called a tensor product?
Yes, tensor product. Tensor product. Yes. In physics textbooks, you will call it tensor product. Mathematics, you will call it outer product. I'm not going to call anything. I'm just going to say it's a tag. Okay, is that?
Yeah, I never knew that was the same thing. Like two vectors next to each other because it makes it diagonal.
Yes,
right?
exactly. Yeah. So that's all. So because there are 9 components to it, right? So A1 has B1, B2, B2, so there are 9 pieces to that. So it's a matter of arrangement of how you write it. If it's a tensor product, you take the transpose of one and put the call. So for example, outer product of two vectors would be this. This would be equal to, so you want to write this as A1, A2, A3, and B1, B2, B3. Right? That's your vector product. Again, if you were to get this all multiplied, so this is A1, B1, A1, B2, A1, B3, and A2, B1, A2, B2, A2, B3, and A3, B1, A3, B2, A3, B3. So this whole combination, that's the 9 components, all possible arrangements of A and B. That's the outer product. That's what we will write as A times B. There's nothing in between. Right? That's what we will. So this is scalar product, vector product, and this is a dyadic or a tensor. Right? So here we are going to use no operation at all in between. So in that sense, we already have two vectors, two basic vectors, and we want to evaluate what is the dyadic structure built out of a gradient operator acting on the position vector. Okay, so that's what we want to do. You can think of it like this, but let me, let's do it this way, right? So this is equal to, if you notice, I have a dy dx, the x component of this, right? So that's x. I have a dy dx of y. This is operation, right? And this is dy dx of z. That's it, all the components. D by dy of x, d by dy y, d by dy z. So that raises the question, what is the derivative of x with respect to x itself? What's the derivative of x with respect to x itself? So this is a matrix now, right? These are the 9 components of this quantity. What's the derivative of x with respect to x itself? 1, right? That's 1. What's the derivative of y with respect to x? Partial derivative. 0. Right? It is 0 because y doesn't have any x, right? As far as that's concerned. There is no x in that, so that's 0. Z, that's 0. This is 0. That's 1 again. 0, 0, 0, 1. That's a unit dyadic. That's unit dyadic. Even though I have actually done this for rectangular coordinates, this is a much more generic statement. This is actually always the case. Okay. So a gradient operator in any coordinate system and operating on the position vector in any coordinate system will always give you the unit dyadic in that space, which means that this has something to do with the completeness. Right? This has the information about the completeness statement. And yes, question.
That symbol wrapped in a matrix, is that a 1 or an I?
This is a 1. I typically write it as a 1. I mean, identity. That's also perfectly fine.
Yeah,
that's okay.
That's how I saw it.
Yeah, that's okay. I think in matrix algebra you would use this as a bold I, suppose. That's perfectly fine. But I will use 1, so yeah, if that helps. As far as idea goes, there is no difference. But I am going to be using 1. That's the way to answer your question. So, so that's good. If it's an identity matrix and if it's a completeness statement, it usually has the information about what's the dimensionality of the space, right? Like if it's a completeness relation, then we should tell how many vectors do you need, right? So there are 3 of them. And the easiest way to do that is to take the trace, right? If you take the trace of this quantity, you will get 1 plus 1 plus 1, 3. And that's the dyadic statement. So that means to say what should I do here with this equation if I want to take the trace? And you will notice that if you were to take the divergence now, so notice this is not a divergence curve, nothing, that's no operation there. This now, right, divergence of R. Now this is a sum, right? A dotted with B, that means this is d by dx of x plus d by dy of y plus d by dz of z. That's exactly equal to 3. We can also do? What is curl of R? Or actually, there's another way of looking at this. Instead of doing it like this, that's perfectly fine. There's nothing wrong in there. You can also see this as I hat d by dx times x dotted with x, and then you dot it with I, right? I dotted with I. It's better. So explicitly see this. I d by dx plus j d by dy. Like in this case, it's straightforward, but I want the next statement to come out of this. So this is k hat d by dz acting on. Now there is an operation dot. This is xi plus yj plus zk. But if the derivative x doesn't act on the unit vectors, which is not the case in all the coordinates. The derivative operators, the unit vectors could change with position. So this operation not acting on I is not always true, but in rectangular coordinates it is. Now I dotted with I is 1, I dotted with j is 0, I dotted with k is 0. So that gives you 3. But now if it was a cross product, right, I crossed with I is 0. But what about I crossed with j? That's k, but then derivative of x with respect to y is 0. So whenever the cross product survives, the derivative kills it. Whenever the derivative survives, the cross product kills it. So this is actually 0. Curl of R is 0. So this is the most important statement here. We will use this all through the course. And as an extra credit, what I want you guys to evaluate, probably last few minutes. So another operation I can define is what is gradient of R. This is a position vector, but that's not a vector, right? That's a magnitude of R. So the question is, what is this equal to? That's the same as the gradient operator acting on x squared plus y squared plus z squared. Any guesses of what this would be? R hat, yes, because it is a surface. So x squared plus y squared plus z squared is equal to constant. That's the equation of a sphere. So it has to be perpendicular to that. So I want you guys to evaluate this explicitly, or let's say I hat d by dx of square root x squared plus y squared plus z squared plus j hat. In some form, I have done this in another lecture probably. So evaluate these derivatives and show that this actually is equal to R hat. So that's extra credit. So two quantities which will be most important in this whole course is this is a unit dyadic and this is R hat. Just with these two equations alone, we will be able to do a lot of vector algebra. We will be able to do a lot of manipulations of vector equations just with these two relations. And I'll stop here. Thank you. Any questions or comments? That's all.
Meeting after this.
Yeah, sure. If that's